Final part of lesson 38, we're going to go over some examples that we didn't have time for in class. The first one on here, log base 2 of 64, is similar to what we saw in class. All I want you to do when you're told to evaluate an expression is just do the math. It's just like if it said 8 plus 4, you would just turn that into a 12. Log base 2 of 64, the exponent that makes it 2 becomes a 64. If you don't know it off the top of your head, that's okay. You can just count. Count by products of 2. 2, 4, 8, 16, 32, 64. We're up to 6. Great. Moving on to the next problem, this is where order of operations comes in. And one of the nice things about order of operations is that it never changes. Ever since you learned it correctly, you do grouping symbols first, then exponents, then multiplication, division, then addition, subtraction. We will always follow those rules. The logarithm is the inverse of an exponent, so it fits in the same place as an exponential. So that means that we have to, in this case, where we have subtraction and multiplication and a logarithm to evaluate, we're going to have to follow our order and do the logarithm, which is kind of exponent, first. So that means I would turn this log base 4 of 256 into a 4, because 4 to the 4th power is 256. But I haven't changed anything else. So this is 3 minus 2 times 4, which is 3 minus 8, which is negative 5. Looking down to the bottom here, this is going to be an important tool we're going to use a lot this unit. Since logs and exponentials are inverses, when you do one to the other, they cancel each other out. Just like the square of a square root, or the cube root of a cube, or the product of a quotient. They always cancel each other out. So the same thing will happen as long as you have the log and an exponential of the same base. So log base 6 of 6 to the 8th cancels out. That's just equal to 8, which logically makes a whole lot of sense. Log base 6 of 6 to the 8th means the missing exponent you need to make a 6 becomes 6 to the 8th. Well, that's a pretty silly sentence to say. The exponent you need to make a 6 become 6 to the 8th is obviously 8. And it works the other way too. 3 to the log base 3 of 21, the exponential with a base 3 and log with a base 3 cancel each other out. So you're left with just 21. And again, logically, that makes a whole lot of sense. Log base 3 of 21 is some mystery exponent that if you were to raise 3 to that power, you would get 21. Well, now I'm raising 3 to that mystery exponent, so I'm going to get 21. We also need to learn to solve some equations with logarithms, and the ones we're going to work with today are all going to be very simple. All we need to do is use the exponential property of equality. And this is something we mentioned last class, this idea that because of the exponential property of equality, that b to the x equals b to the y if and only if x equals y. That was the exponential property of equality. One of the things we said about that is you can exponentiate both sides of an equation and your statement is still true. If I started with x equals y, I can turn that into b to the x equals b to the y. I've exponentiated both sides and the equation is still true because of the exponential property of equality. So what we're going to do with that is take log base 5 of x to the sec equals 2 and say, if only this was 5 to the log base 5 of x, then my log would cancel out. Well, I can make that 5 to the log base 5 of x as long as I exponentiate both sides. So the reason to do this is to say the 5 to the log base 5 cancels out, and on the other side I can evaluate 5 squared. Looking at number 22 here, that works even if my base is an exponent. Now, this does create a bit of a domain restriction. We've said that the base has to be positive, and it can't be 1. But as long as that's true, I can exponentiate with a base of x here, and my x to the log base x cancels out. So I get 9 equals x squared. And if I solve that, we know that x equals plus or minus 3. But because of the domain restriction, we know that the base of a log or an exponential cannot be negative. So in this case, x can't be negative. It can't be 0 either. It's got to be greater than 0, which means I will ignore the negative 3 solution, and I will say that my final solution is just x equals 3. X equals negative 3 would be an extraneous solution. This works even if the equation gets a little bit more complicated. I can exponentiate both sides to get rid of the log. What's important is that this only works if there's a log on both sides, if the logs on both sides have the same base. Because now exponentiating with a base of 5 will cancel each other, cancel the logs out. So I have p squared minus 2 equals p. And we can solve this using our pretty standard process for solving a quadratic. This one factors. So we can split and solve with the 0 product property. Sorry, that's supposed to be a plus sign. And so p could equal 2, or p could equal negative 1. But we're checking our domain restrictions because of this right here. If p is inside of a log, we saw early on in today's lesson that the domain of any log is that the argument has to be positive. You can only take the log of a positive number. So this means that p has to be bigger than 0, which means we can cross off that. And so our only solution is p equals 2. This idea of exponentiating both sides to take away the log on both sides, if the log happens to be of the same base on both sides, it's kind of long-winded. So we have a log property of equality to kind of shorten our work on that. And it's just like the exponential property of equality. Log of any base of x equals the log of any base of y if and only if x equals y. So just like we can just ignore the exponent in an exponential equation, as long as the two bases are equal to each other, we can do the same thing with a log. And the very last skill for today's class is something which other math teachers love. I'm not quite as fond of, but I'll show you how to do it anyway. Because the definition of a log, where we came from today, was that a logarithm is the inverse of an exponential. X equals b to the y is where we started from when we made our first graph, and we just gave it a new name, y equals log base b of x. If it's just the new name of something that we already had, that means they are equal to each other. They're the same thing. So anytime we have an exponential equation or a logarithmic equation, we can rewrite it in the other way if we prefer. It's a trick which, when you get to calculus, you'll kind of use this trick a lot. It's easy to do to make this conversion. If I wanted to say log base 8 of 1 equals 0, remember the idea of log base 8 of 1 means the missing exponent that makes an 8 become a 1. So if I wanted to rewrite this statement as an exponential, I would say that the missing exponent that makes an 8 become a 1 is 0. And there is a cute little shortcut you can use to kind of rewrite this. If you start from the base, because the base of the log is the base of the exponential, and sort of make a big wide circle around, that's our exponent, 3 to the 5th equals 243. And that'll work for any exponential or log equation that you want to turn into an exponential equation. 2 to the negative 4th is equal to 1/16. And it works the other way too. If I want to say that 10 to the 3rd power is equal to 1,000, that means that the log base 10, the exponent I need to turn a 10 into 1,000 is 3. I'm just restating the exact same fact in the other direction. And again, you can use the little wide circle like that, starting from the base. If 9 to the 1/2 is equal to 3, I can make a swing around. Log base 9 of 3 is equal to 1/2. Log base 9 of 3 is equal to 1/2. Log base 5 of 625 is equal to 4. And while I don't think this is the most important skill we have when we talk about logs, sometimes it does help you to kind of understand what's going on in a problem if you can switch back and forth between logs and exponentials.